Okay. Okay. We are testing all the connectivity because all the talks are also simultaneously transmitted by Facebook and YouTube. So after the technical details, we will start. Morning, everybody. Let's start today, this morning, with the second schedule for the symposium celebrating the 50th anniversary of our university and the 200th anniversary of the pioneering work by Sadi Carnot. This time, Professor Magdaleno Medina Noyola from the Universidad Autónoma de San Luis Potosí. Let me introduce you briefly the academic career by Magdaleno. Magdaleno is a prize and award collector since prize for his master thesis in science, his Marcos Moschinsky Medal given by the Universidad Nacional Autónoma de México, awarded by an award for the Mexican Academy of Science, by Alexander Humboldt Fellowship, and also one of the Mexican researchers awarded with the big prize in Mexico given by the president of the country. Is the National Prize of Science delivered in 2013. And many citations for his papers, over 100 papers published along his career. It's for us very honored that Magdaleno today give us this talk to celebrate our university. So, Magdaleno, go ahead.
Okay, good morning. I'm not used to have the microphone and so I will do my best. First of all, Ruben, thanks for the introduction, completely undeserved. You're just saying that I'm very old and so anyway, let me start my talk. I will explain to you what I mean by the title. If you're confused, I am. So I will start with that. But before, wait a minute. Eric, you were right. It doesn't work. Yeah. But let me say, I'm really honored for this invitation. The organizers know that I have a very deep gratefulness for this university. I think that one time of my life was attached to this place because in the 80s, I came back from the United States, and most people had to have more than one job to complete the money to pay the fees for his students and his school fees and so on. And that was great. So my memories are just like beautiful, like this photograph of one of the patios of UAM. And it was a really nice time also academically and as a faculty. I remember this manual for thermodynamics written by Professor Francisco Medina Nicolau and other people, including Luz Maria. That was a small community, mostly in the area of teaching and doing bootstrapping to do also some research. And so I have that time of my life as one of the most precious ones. So that's why I'm really, really very grateful for this invitation and so I hope that one will have many more anniversaries. So happy anniversary. Okay, now let me go to my talk. The main thing that I want to talk, one of my collaborators, I didn't arrange my talk in the way he did. He said, this time I'm not going to talk about science. This time I want to sell you something. And what he wanted to sell is in the second part of in the third topic of this list. But I mean, I couldn't refrain from going through some antecedents. So I want to talk about equilibrium states versus non-equilibrium states. And then what are the main challenges in a certain context of those non-equilibrium states that become so permanent that is the kind of states in which matter is in the most common matter. And that means the concrete in the walls, your clothes, where you are sitting, what you ate this morning, and so on. The matter that you interact with mostly is really in certain kind of non-equilibrium states. And that's what I want to contrast. And then what are the challenges? Okay, because there are many people who are working in this field. And at least for me, I never understand when will we say we're finished. We now understand. And so that's what I want to say in the second part of the talk. Then to explain to you some efforts that we have made in going in that direction. And in the end is what we are working right now. Is basically the plan of the talk. Okay. I was going to say that matter, we was particularly physicists, when one comes to physics because we would like to be like Einstein and like to do astrophysics and so on, because the borders of science is in the very big, in the very small, and what I would like to say is actually the matter that is in what we are made of, what we interact with, presents really fundamental problems. But somehow physics renounced to attack those problems, and instead, I mean, there are reasons for that and good reasons. So anyway, the states of matter. We know about gases, liquids, and solids since one is in elementary school. And later on, we learn what scientists have done to understand and describe with more precision. And the best example the first example are gases, okay? And you have the most fundamental approach to knowledge, and that is touching, measuring, experimental contact with what you are describing. And that's what these people did. And the work of these guys go all the way to our secondary school. We are taught about Boyle's law and so on, right? So these people did the most fundamental work in understanding gases. And then they not only did that, but they put together partial discoveries to come up with a nice, beautiful equation and that synthesizes the behavior of gases. And so everybody knows, particularly chemists, engineers, physicists, and so on, the equation of state of ideal gases. So this is like one approach to understanding. There is a second complementary approach, and that has to do that we would like to have a molecular image of that, right? And many of you probably remember those arguments given by Maxwell, Boltzmann, counting how many, if you have a gas, and the molecules collide against the walls, and then you measure the momentum per unit time, and that's the force, blah, blah, blah. And all of a sudden, you have, let's say, a molecular understanding of this experimental fact, right? This is a little bit like the simplest model of understanding, let's say, using physics. First of all, you measure. Second, you try to explain using a molecular image. And this, let's say, these people, by the way, Maxwell, but particularly Boltzmann, he was happy understanding gases, but he was far more far-sightseeing, seer, or whatever you say it, because he actually gave us the really robust fundamental principles that will help us understand gases and liquids and solids and so on. And okay, there were fundamental principles with universal, and that's what is common to all of us in this meeting, the laws of thermodynamics. To me, the most important one is the second law. That is completely above mechanics or above anything. It's really a fundamental, one of the most fundamental, it's the most fundamental law of, and one of the consequences is that you synthesize your knowledge of a system when you know the relationship that gives you the entropy as a function of the extensive variables, okay? Probably I'm repeating some concept that we heard yesterday, which is good because we are talking about basically the same things. And then this is fine, but the second law tells us that equilibrium states maximizes this function when the system is closed. But the most fundamental, complementary fundamental principle, it was given to us by Boltzmann, and it is writing the entropy as a function at the logarithm of the number of microscopic states, and that is counting how many microscopic states you have first to say what is to describe mechanically the system, and you write the Hamiltonian, and then say count how many states are between energy E and energy E plus delta E. That's something that most of you did as exercises in some of your courses. But anyway, this is perhaps this principle together with the maximum entropy principle is what you need to understand matter, at least when matter is at an equilibrium state. So we can say equilibrium states are solutions of this equation. The differential of the entropy equals 0, right? And I want to say this because physicists like to write equations when you have a fundamental principle. If you want to understand electricity and magnetism, Maxwell's equations, right? If you want to understand thermodynamics at equilibrium, it is this. And when you apply this to, this is a common exercise that you do in your courses of statistical physics, calculate W, take the logarithm and blah, blah, blah. And now you get the properties of an ideal gas, right? I'm saying all of this mostly for students because they should recognize here some concept that you are struggling right now in your courses, I guess. And if you apply the same principles and write the Hamiltonian and so on for a system that is made, when we say the Hamiltonian, that means that you have to say my system is formed by n particle, and every pair of particles interact with some pair potential, pairwise force, for example, may be more complex. But if you give the interaction, then that allows you to calculate W and then take the logarithm and blah, blah, blah. And then you discover that a system like this made of little balls will have not only gases as one of the thermodynamic phases, but also liquids and also solids. Of course, solids mean, and if you don't want to deal only with balls, but also with rods, then you have also phases like liquid crystalline phases pneumatic, kinetic, and so on. And you may also start to say, oh, this is fun. Now, what happens with worms? And with worms of different colors, these are block of polymers or these kind of substances represented with this. And you apply the same principle, maximize the entropy, and you end up discovering a really crazy variety of different phases. So we not only have gas, liquid, and solid. We may have liquid crystals and microphase separated structures, right? So that means that if I take all the possible Hamiltonians in the world and I play this game, I can, generate the catalog of all possible equilibrium states. So, and let us put these equilibrium states in a basket. And this basket is actually, each of the members of this set is a solution of those equations, of the equations of the maximum entropy. And the basket that I'm talking about are your books on thermodynamics and statistical thermodynamics. That's where these states live in. Okay, this is my naive, simple-minded way to describe equilibrium states. The solutions of a given equation, this one, right? So at least physics has the equation from which we can understand the states of matter, at least equilibrium states of matter, which is beautiful because as we said, we have gases, liquids, and solid, and we can go from one phase to another phase. And the problem how to cross this is the kinetics is still a fundamental problem, and also understanding details. But the basic idea of how matter behaves is really, let's say, can be represented in this way. And of course, if we want, and this is something that we heard about, we have quasi-static processes. That's the way to go from one equilibrium state to another equilibrium state, but that takes time. And your student doesn't have sufficient time to get a beautiful crystal when he cools the liquid, and he, let's say, instead of a black pattern, sometimes he may be in a hurry and he will not get this, but instead, he has something which is not crystalline, but it's amorphous, but it's a solid and hard material like the crystal. And of course, we are talking about glasses, for example, window glass or whatever. And the main difference is that one is crystalline and the other is not. But that's the structural difference. But the most fundamental one is that the crystalline one belongs to the basket that we were talking about a while ago. And it happens, however, that the glasses, we see them in many areas. That's what we started saying. And not only, let's say, glasses, these compact hard materials, but if you pull the fluid within the solid liquid coexistence, and you do it also very deeply and very quickly, you will not get this beautiful gas liquid phase separation, but instead you get a mess, okay? This sponge-like kind of structure, and it also lives forever, okay? It's a gel. And so these kind of structures are quite familiar. The yogurt we had this morning is related with this kind of structures. So we have an alternative catalog of states of matter. And these are non-equilibrium amorphous states of matter. It's mostly solid or with rigid properties. And these also constitute a set, well-defined set, in the sense that they don't, the main point, they are not stationary. They exhibit aging. The ones in the previous basket, they don't. They decay sort of exponentially, and once they stabilized, that's it. There is nothing that in a week it is changing in a year and blah, blah. These materials, you measure something today, something in a day, in 10 days, in 100 days, in 10 to the n, and it will keep changing, okay? And that's why I was asking yesterday, that means that you need logarithmic paper to plot the properties of these kind of materials. That's one thing. The other thing is that when the system is at equilibrium, it doesn't matter how you prepared it. As long as it is in the same temperature, density, blah, blah, is the same material always, okay? And that's not what happens with these materials. So these two properties are the ones that tell you this guy is not at equilibrium, okay? So it belongs to this different basket. So we have these two complementary sets of states of matter. The first one on the right, we understand it perfectly because these are the solution of this equation. And now the question is, I start with the second part of it. What are the main challenges in the field? I use this introduction to tell you, of course, if these guys are not children of that equation, then whose mother, which is the equation they are solution. And that is, let's say, the fundamental challenge, the first fundamental challenge, okay? A second challenge is something that if we don't speak with engineers, then we are not aware of that. But these guys, this is something that mechanical engineers and particularly companies, glass companies, steel companies, and so on, they produce time temperature transformation diagrams. And that is very simple. This is, for example, imagine that you have silicates, borates, and blah, 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 powders or stones or whatever. You heat them up, make a liquid, a fluid, which is a mixture of those components, and then you cool it. Cool it at some point, you cool it, let's say, to 800 degrees, okay? It was at 2000 degrees or whatever. You cool it, and let's say at 800, and then take your watch, and you observe the system. It's a liquid, it's a liquid, it's a liquid. All of a sudden, it changed to a transparent glass, and eventually to a crystalline glass. And if I do that to 900, then I see this and so on. This is like industrial property of companies, okay? Because this is a summary of how their material behave. And this is what the engineers use to do technology, okay? This is with hard materials, but this is a paper by this group about 2010, I guess, in which what they use, they take laponite, a clay, and a little bit of that dissolved in water, and let's say the horizontal axis. Oops. Sorry. Okay. The horizontal axis here is concentration. How much of this powder you put in the water. And again, you take your watch and see it is fluid, it is fluid, it is fluid. All of a sudden it becomes, its phase separates, it gets a gel or it gets a glass, okay? This type of phase diagrams, you might, it's like a phase diagram, except that it's not an equilibrium phase diagram. This is time. And in the previous one, the horizontal axis was time, okay? Let's see. This type of information, let me put it this way. This for clays and this for glasses is very much the raw experimental measurements. It's sort of similar to what these people were doing with respect to glasses. Go and measure and be precise in your measurement. And do even better. Can you generate some can you see some pattern, empirically defined patterns, what you observe? Like these guys eventually said PB equals nRT, okay? We are now exactly in this time. We are having a huge amounts of experimental information, and there are nice, beautiful empirical models that tells you these glasses or these gels obey this empirical law. Okay. So the other fundamental challenge is we need the analog of what these people did with the molecular understanding of these empirical findings. Okay. And these are the two challenges that, in my view, you should answer them. If you answer them, then that's it. I mean, or you are starting to have progress, and so anyway, I should tell you, and to do that, you have to start from this fundamental principle. And I will say that I'm sorry, but the time is not enough to explain the details. Okay, so let me tell you the short answer to how far have we gone with that. And the short answer is that this is a PhD thesis from Universidad Autónoma. That's somebody asked me this morning about autonomy of the universities. This university was the first autonomous university in the country, and is celebrating this year the 100th anniversary of autonomy. And later on, the national university became autonomous. And it's not the relevant part of it is that this is a PhD thesis presented by this guy, Pedro Ramirez, and these are the equations that if you solve them, you answer both of these two challenges, okay? So sorry to be so rude, and just to tell you, these are the two fundamental problems, and these are solved by solving these equations, right? That's why I said I'm not being very serious in explaining the details, but I mean, I couldn't be able. Let me also, for the students, let me tell you a little bit about Pedro. Pedro started to work for his PhD with me when we had a theory of dynamic properties of systems. It was a first principle theory that you had to define the pair potential between the particles and so on, and then you could calculate diffusion coefficients and so on. And I asked him, can you do that? We had done already with hard particles and soft particles, and I asked him, actually, he did the soft particle, and also say, and add attractions to see what the effects are. And I thought this can be done. It's just a matter of hard work, and he will get it. And then I said, if you get these two problems, you will get your degree. Without honors, but you will get it. Now, beyond that, that will be a measure of your ambition. And this guy, after a year, he had those two problems solved and published and so on. And then he came to me and he said, listen, okay, I don't know why I put this, but anyway, this is the theory that he developed in his thesis. But what I wanted to say about this guy, he then came to me and he said, okay, now I have about a year and a half or 2 years still left, and I would like to do something else. And he said, you once told me that when you were a postdoc, your boss asked you to calculate certain properties using a certain approach. And he said, there are these beautiful experimental results that I will come to them a little bit later. And he actually made me to go back to what I had done in my postdoc, and these equations came as a result of applying the methodology proposed by my boss when I was a postdoc. I will come back to this. So anyway, we can view this as a machine, just like the Boltzmann principle and maximum entropy. You put in the Hamiltonian, and then you get phase diagrams, structural properties, dynamical properties, and so on. Okay, now with these equations, you can also give the Hamiltonian and then give the preparation protocol, okay? And as a result, you will get the same type of properties, but as a function of time, of the time after the cooling or the way you prepare. Okay, there are publications. By this time, when I made this list, there were 24 publications. There are like 30, starting from 2010. The first one and the thesis was published in, the first publication was published 14 years ago. And okay, let me say, not to derive or anything like that, but just to give you a flavor, how we came up with this, building this theory. These are the experiments that this guy saw in this Journal of Physical Chemistry paper from 2008. Okay, that's when he finished his first two assignments. And what you see here is a colloidal suspension of particles of about 1 micron in size. Half of them are charged positively, the other half are charged negatively with roughly the same magnitude. So it's a colloidal model of sodium chloride in water. Okay, but this one you can make pictures with confocal microscopy, and this is what you saw. You did the analog of cooling, see, and this is the response of the system. The particles here, they don't care about who is his neighbor, but after you cool it, they immediately try to make pairs and then clusters, and this is the process. Now, if you do a Brownian dynamic simulation, you see exactly the same type of story. And this is what this guy said, this looks fascinating. And these guys summarized what they were saying by plotting the static structure factor. And that is, instead of the black peaks, you have the pattern of an amorphous material, and you measure the intensity as a function of the distance from the initial ray. And this has to do with the wave vector. And this is, let's say, the type of property that you could record. And this will be the static structure factor of a here, like system, very dilute. And as soon as you pull it, then this grows a little bit. But the most interesting is this little peak here. And that has to, this is at lower wave vectors than the mean distance between particles. And that means that they tell us about larger distances. And that really means the build-up of the clusters, okay? So the question is, can we write a time evolution equation for this object? That's what I mean. That's the obvious attitude of a theoretical physicist. Can I write the time evolution equation? Oh, this is the guy that was my boss when I was a postdoc at the end of the 70s in UC Davis. This guy really knew. Unfortunately, he died very early, but he was a really wise man. And his book is really, there are many things that people have not uncovered from what he wrote in this book. So anyway, I was extremely fortunate that he taught me irreversible thermodynamics and these kind of things. And he was, let's say, from him, I understood that the guy who knew much more and the most fundamental things, that was Onsager, okay? Onsager was given the Nobel Prize in chemistry, not in physics. Physicists don't like Onsager's attitude. And for one reason, is that he doesn't start from the Hamiltonian. And a bona fide physicist has to start from a Hamiltonian, okay? And sometimes that is a terrible burden, okay? Instead, this guy was more interested on fundamental limitations imposed by mathematics, by symmetries, by these kind of things. And that is far more general than physics, right? And so anyway, one of the main, to me, these are, after the second law of thermodynamics, this is the most fundamental physical principle dealing with the behavior of matter. And these are what I call linear laws, in which these are the time derivative or the time change, the rate of change of the extensive variables, or the deviations from equilibrium, decay according to this equation, in which these are the thermodynamic forces. So these are the extensivities, where they were called yesterday, and these are the intensive variables, right? And it happens that there is no transport equation that escapes from this pattern, right? And these are called the linear laws. Now, the first thing that you want to learn is, what are the stationary states of this equation? Again, we are physicists, but we know mathematics. And the first thing that mathematicians ask when they have a question like this, what are the stationary states? Because they are fundamental, okay? And clearly, if the departure from equilibrium measured by the departure of the intensive variables, if they vanish, then this vanishes, okay? So we might say the basket of equilibrium states maps onto the stationary solutions of these equations, So, and that is correct, but it's not the totality, because it happens, the L here, if it was the diffusion equation, L is the diffusion coefficient, okay? And we are taught normally that the diffusion constant is a constant, okay? And it's a crazy thing. Actually, this guy depends on the state. They are state functions. So we should have like the thermodynamic equations of state. We should also have the kinetic equations of state, right? And it may be that this guy may become zero without this guy becoming zero. And that is exactly what happens. And then you have a second family of stationary solutions. But this refuses, because they are not very popular. But anyway, those are exactly the solutions that corresponds to dynamically arrested states. I say, I wish I was said this when I was a young student, because then you would understand something really fundamental. Matter, once they get stationary or approximately, they will bifurcate into two possibilities. This is in no textbook, is in no paper at all. It comes, I mean, this should be there. I mean, Gonzaga said this in the middle of last century. But then people were not as interested as now on glasses and gels and so on. But Gonzaga gave us these theoretical fundamental tools to understand matter. Okay, these equations correspond to the time evolution of the mean value. What we measure is really mean values, okay? But physical properties, extensive physical properties, always fluctuate. And if you don't talk about the fluctuations, then you are only having one part of the story. And that is, again, something that has happened to the community. I mean, that's not complete. You have to go to the full distribution, probability distribution. Now, I know that we have to do that, but I'm not brave enough. So instead of that, we said, okay, don't go that far, but at least the covariance, right? Because it happens that the destruction factor is a covariance. So we wanted to drag the covariance into the discussion so as to have an equation for the time evolution of that object. And I will not go into much more details, but what we did, we had to extend Gonzaga's theory. Everybody says, yeah, but that's macroscopic, it's like thermodynamics. It doesn't talk about atoms. It doesn't talk about their potentials. I mean, it doesn't talk about that because you don't want them to talk about that. But it's no big deal to include molecular resolution, both the space scales and time scales. And that's what we did previously. And by the way, I want to mention this paper let me see if I have it larger now. Last year, they asked us to write a sort of a review paper on the fundamentals of these kind of things. And for example, we don't even talk about Onsager in the title, but instead of that, we talk about, Onsager-Maglub theory, which is a theory for the fluctuations, okay? And it is our version that we made it not only, let's say, space and time, non-local, and also far from equilibrium. So anyway, if somebody's interested, it just came up at the end of last year. And so we have one equation for the mean value, one equation for the covariance. And I want to say this because if you apply this to your extensive variables is the local density, then the local density, we need an equation for the local density itself. And it happens to be just Fick's law, basically, okay? Except that the diffusion coefficient or the mobility, this is a state function, okay? And then we also have to drag the time evolution equation for the covariance. And within this formalism of Onsager-Maglub theory, then, oh, by the way, this equation maps onto what is very commonly known as dynamic density functional theory. Is a completely independent area of statistical physics, but this is contained in this equation. But now we also have the time evolution equation for the covariance. And this is what we were looking for, right? Now, the point is, however, that there is this mobility that we are now saying that this guy is a state function, so we need an equation or a manner to calculate this guy. And I think that I'm extending a little bit too much. So anyway, this equation for the covariance looks like this. And in terms of the structure factor, what you measure in light scattering or Newton scattering, okay? And these are what we wanted to model this. Now we have the questions. The question. This object that appears here is the second derivative of the free energy. The second derivative, the first derivative at the density here, and then the second derivative at the density here. So that is a 2-point. There is a distance in between. You can include the distance, or else you include the Fourier transform variable, and that is the wave vector k on which this guy depends. But anyway, this comes from your fundamental equation, your fundamental thermodynamic relation. This is an ingredient here. You really have to solve first the equilibrium problem, and then you can use these equations. Let me, here also you can see that there are two kinds of stationary solutions. One, the equilibrium one, in which the bracket on the right-hand side there becomes 0, and that's the equilibrium condition for the structure factor. And else, the stationary solutions that become stationary because the kinetic component is the one that becomes 0, right? Let me see, how am I doing with time? I must finish now. So let me also say that in glassy and gel materials, there are phenomenological laws with respect to the aging. And one of the things that is really well known is that, and this is called the Tull-Narayanaswamy-Moynihan model. It's a phenomenological model. And they say lots and lots of data for aging can be represented like the solution of this equation. which is a linear equation, except that this relaxation time depends on state, right? And then these very same guys say, if you make a change of variables to this, say, and they call the material time or inner time, and that's what I was wondering, that must correspond probably with the natural time we heard about yesterday. If you do this change of variable, then this linear equation becomes really linear, right? And this is a way to say there is a transformation that put this complicated data into something more, something simpler. As it happens, this is another paper that appeared at the end of 2022, where we approached this problem because it happens that these equations, particularly the one for the structure factor, I made a mess. Yes. But then, let me say, if you take this equation, it happens that it has exactly the structure of the Tulnarayanaswamy Moynihan model. Of course, we didn't appeal to that. We appealed to Onsager's general formulation, and this is what comes out. And let me just say, the topic we are talking about now are viscoelastic properties, because the quantities that enter in these equations can be measured using neutron scattering, light scattering, which is a more specialized kind of instrumentation, whereas a rheometer is everywhere. And let me say, some illustrative applications. I know that I have to finish, and so I will be. These are the first experimental data that provoke all these developments, and this is, let's say, a theoretical interpretation. You assume that you have the Hamiltonian, and then you solve, and this is a sequence at different waiting times of the structure factor. These are simulation data by the people downstairs, and these are the corresponding theoretical results. And this is the comparison between them. And this was one of the first achievements of the theory, and we were convinced, Jesus, this is nice. We didn't put too sophisticated stuff into the theory, and it performs amazingly. And this is, for example, a visualization of what happens when you, I don't know, no, I cannot probably, you know. No. Oh, okay. This is a visualization of the real physical phenomenon that is going on. The heterogeneity is when you have a gel. At first, it takes some time, a latency time. Nothing happens. And all of a sudden, they grow, and then they get arrested. And let me run it again, because you see, nothing happens, they grow, now nothing happens again. And after this, I wanted to show you this experimental data from a group by Professor Stefan Egelhoff, who passed away just recently, PP. And this group had measured, let's say, the gas-liquid separation of lysozyme. Lysozyme, a protein in solution, there is an attraction due to van der Waals forces, and if they put some additive, then these attractions can be weakened or can be increased. And if you do that, then the binodal line is shifted tremendously. But the dynamic arrest line, the gel line here, that remains basically unchanged. And this is the theoretical analog, and it has exactly those that pattern. And I think that I have to just to mention, the viscoelastic property is a really beautiful subject. And let's see who are here. Ricardo, can you stand up? Ricardo and Orlando, they came from San Luis Potosí. They were curious about it. And these are the ones who had the guts to do the derivation of the theoretical derivation relating viscoelastic properties with the properties that come out of the theory. And Gabriela, and there are 4 people who are coming and they are here. And it is fair to say the merit is theirs. Okay, it's really beautiful work that they did. Unfortunately, this is a system with attractions. And then you do a quench, a shallow or a deep quench. And then you see, as a function of waiting time, what is the response in the elastic moduli. And this is something that could be calculated with the work of Ricardo and Orlando. And this was done by Leticia, who is right now at Northwestern. And these are the theoretical predictions for this moduli for different depths of the. And this is where we see that there is a latency time, and then you have action. And this is exactly what is measured in this paper in the group of Leheni and other people in the States. And with this, I think that I have to finish just by mentioning that this theory, so far, every prediction is immediately tested with an amazing predictive capability. And with this, there was a paragraph in the abstract that if you read it just and laugh as much as you want. But it has to do with the following. This group, it happens that most of these people do not have a position. And there is no way that they will have it with the conditions of the country. So some friends of us in the States, they told me, how are you doing with your group, the work of your group? And one day, and I always say, well, it's really nice. Nobody cites us, but it's really beautiful, and blah, blah, blah. And then but they understood what we were saying. And one of them who works in a company in Silicon Valley said, listen, I told of what you are doing to this colleague of mine, and he is friend of a former CTO of a major glass company. Would you be willing to speak with him? And all what they wanted was to ask this CTO to ask me what is exactly what you are doing and blah, 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 or what your group is doing. And then the question was, do you think that this is of any relevance in the glass industry? And the immediate answer was, this would be terrific, because there is nothing first principles. There are simulations, there are phenomenological models and so on. That would be really nice. And it happens that these guys said, why don't we make a company? And the purpose of this company is to support the group before it dies away, because I mean, more than that, I shouldn't say, but since it was in the abstract, this is what we meant to say. And basically, the way these guys know business, I will never be able to sell an equation. And these guys say, okay, we will sell one equation at a time. And basically, what they say, normally, the technology of concrete, of plastics, and so on, is just trial and error. So they don't have a reliable modeling tool, okay? And these equations are becoming a modeling tool. I hope that these guys are lucky and that we do not die of, the group will not die. And I just wanted to share this, and I think this is it. I mean, this is the advisory board. We have people from high-tech industries and so on. So I really hope that they will be able to raise money and let us keep on doing the work we have done so far with only enthusiasm. And with that, I thank you very much for your patience and for your attention. And I think that we are open for questions in case there are any. Questions? Comment?
Okay. Sorry. Peter.
First of all, thank you for a lovely talk. But you mentioned a lot of it comes from, or a lot of your results come from the Onsager relation, which is a near equilibrium only relation. I wonder if you would comment on that.
This paper that was published at the end of last year, or beginning of this year, that summarizes the answer to your question. But in short, as you say, Onsager's and Onsager-Maclub theory is for equilibrium conditions, deviations away from equilibrium, okay? And what we did was, first of all, to extend it, and it is also local in time. So there is no memory, for example. Putting memory is just a mathematical triviality and can be done. And Joel Kaiser, who was my guru in UC Davis, he said, of course, Onsager knew that. He simply didn't think it was necessary to say it. So that was not complicated, including also the molecular resolution, a spatial molecular resolution, again, is a minor thing. What is not a minor thing is to get away from equilibrium. So that's why what we did was the following. Onsager's theory is just Langevin's theory, Langevin's equation. Langevin said the velocity of a Brownian particle obeys a linear regression equation with fluctuations. But it happens that that's a mathematical model, okay? So you could say differently. Langevin's theory is just saying that the velocity of a Brownian particle behaves as the Ornstein-Uhlenbeck mathematical model. Now, and that is a model for stationary conditions. And equilibrium is stationary, that's why it works near equilibrium. Now, Onsager, what he did is really say what Langevin said about the velocity applies to any extensive property of a thermodynamic system. So Onsager's theory is saying all thermal fluctuations behave as a mathematical model referred to as the Ornstein-Uhlenbeck model. Now, what we did was to say, okay, imagine that you don't have an equilibrium condition, but instead you heat the system and then cool it, and it should come this way, far away from linear regression, okay? Then what we said, okay, this is the mean value comes like this, and fluctuations come around this. So we said, but piecewise, it's just stationary. So we built a mathematical model of a stochastic process, which is piecewise stationary, not equilibrium, but stationary, okay? So all of a sudden we have a mathematical model for really non-stationary process. And now we did what Onsager said. Let's assume that the physical, the extensive properties and the fluctuations around the extensive properties are describable by this mathematical model. So that's the way we get away from near equilibrium. I'm sorry, I know that this is a little bit technical, but.
Another question? Comments? Well,
I'm around, so.
yeah. Okay. Thank you very much for this nice talk. Now, the next talk is given by Leonardo Sigalotti and with the presenter.
Good morning. The next talk will be given by the Dr. Leonardo Sigalotti. Dr. Leonardo Sigalotti is a full-time professor with us in the Basic Science Department of the UAM, of the Autonomous University, Metropolitan University, have the level 3 distinction of the National System of Researchers of Mexico. He completed your university degree by the University de los Andes in Mérida, Venezuela, the Italian equivalence of degree in physics in Trieste, and a master's science degree and the PhD degree in astrophysics by the International School of Advanced Studies in Trieste, Italy. In the 2012, he accepted a position like permanent researcher in the Venezuelan Institute for Scientific Research. In 2014, he occupied the Cátedra Francisco Medina Nicolau in this academic unity of the Autonomous Metropolitan University. He's author and the co-author of a great number of scientific articles published in international magazines, also have been author and co-author of chapters and books in different areas like computational physics, thermofluidics, astrophysics, numerical methods, and experimental fluid dynamics. At the present, have collaborations in many research groups in Mexico and foreign countries. Now he's coordinator of the Energico, a project, a Center CONACYT project in collaboration with several Mexican and European institutions on the construction on the multi-phase software for the improved crude oil extraction. And now, will we talk about on the Sally's entropy and no extensive statistical approach to seismology. Is another topics that he works now. Thank you.
Well, I have this. Well, okay, good morning. Well, I want to thank the several organizers, okay, of this event for having invited me to have a talk. And then, as you may see from the title of my presentation, okay, the topic, okay, we'll talk to you about is, okay, it's an overview, a brief overview, okay, of non-extensive statistical mechanics, okay, based on the Sally's entropy and some of its applications to seismology. Okay, I need to tell you that I'm not an expert, okay, either of seismology or non-statistical or non-extensive statistical mechanics. Okay, as Professor Vargas told, okay, my main line of research is numerical astrophysics and computational fluid dynamics. Okay, then in any way, okay, if I'm here today, okay, it is thanks to Professor Alejandro Ramirez, who have been introducing me, I would say gradually, okay, in this topic, and particularly, okay, in this part, okay, of seismology. Okay, then now, okay, I want to present, okay, my talk is has been divided, okay, into three main parts. Okay, the first part, okay, has to do with a brief overview, okay, on the fundamentals of non-extensive. Okay, sure, I see. Okay, the first part, okay, my talk, okay, is devoted to a brief account, okay, on some fundamentals of non-extensive statistical mechanics, okay, based on the Sally's entropy or SQ entropy as it is better known, okay. Then in the second part, okay, I want to describe some results, okay, from other authors, obviously, okay, about the role played by Zali's entropy in seismology, okay? And finally, okay, I will conclude with some, a few remarks, okay? Then when talking about non-extensive statistical mechanics, okay, we refer to a generalization of the classical, okay, Boltzmann-Gibbs entropy or Boltzmann-Gibbs statistics, okay? And this was necessary in order to correctly describe, okay, the non-equilibrium system with long-range interactions in space and time, okay, long-term memories or multifractal structures, okay? In part, okay, I must say that this generalization was introduced, okay, in 1988 by Zalis, okay, in a seminal paper, okay, where, in order to account, okay, for the correlations among elements of the system at all length scales, okay, and these correlations, okay, led to broad distributions, okay, with power law asymptotic behavior, okay. Then, obviously, okay, a non-extensive statistical mechanics approach, okay, based on Zali's theory, represents a very robust framework, okay, for the description of far from equilibrium systems, okay, having, as I told you before, long-range interactions, okay, long-term memories and multifractal structures, okay, as happens to be the real seismicity, for instance, faulting, plate tectonics, okay, with a special focus, okay, on the mechanism, okay, of earthquake generation. Okay, then I will pass, okay, to, okay, Zali's entropy, okay, or SQ entropy, as it is better known, okay, is given by this expression, okay? This expression applies, okay, to a system, okay, with a discrete number of states, okay? Here, K is the usual Boltzmann constant, okay? The capital W, okay, refers to the number of microscopic configurations of the systems, and the PIs, okay, is a discrete set of probabilities, okay? Here, Q, okay, is a real number, okay? This, which is called, which is known as the entropic index, okay? And it's a real measure, okay, of non-extensivity. In other words, okay, it's a real measure, okay, of the level of instability. Okay, this set of discrete probabilities, okay, will satisfy this condition, okay, and then we say that when Q, okay, approach unity, okay, this Zali's entropy becomes, okay, reduces to the usual BG entropy, so the classical Boltzmann entropy, okay, and then, okay, this expression, okay, we have equal probabilities, okay, well, when all probabilities are equal to 1 over, okay, uppercase W, okay, then the Zali's entropy can be written as follows, okay, okay, over this expression here, okay, so here, okay, and this is the Q logarithm, okay, which is defined according to this relation, okay, and the inverse is the Q exponential function, which has this value, okay, when 1 plus 1 minus Q, okay, Z, okay, is greater than 0 or 0 otherwise, okay. Obviously, when Q is equal 1, okay, the Q logarithm, okay, and the Q exponential function reduces, okay, to the natural logarithm and to the normal exponential function, okay. Now, the non-additivity property, okay, one characteristic, okay, of Zali's entropy is that it is non-additive, okay. This means, okay, the non-additivity, okay, is manifest, okay, by this expression here, okay. For instance, okay, if we have two states, okay, A and B, which are probabilistically independent, okay, then the combined probability, okay, is just, okay, the product of the individual probabilities. Here, okay, I made a mistake, okay, here I should be J, okay. Then the entropy of the combined system, okay, will have this expression here, okay? And this expresses, okay, non-extensivity in the sense that when Q is equal to 1, okay, this term disappears and we recover, okay, the classical form, okay, of the entropy, okay, the extensive form of the entropy, okay? We say that when Q is less than 1, okay, okay, then the combined entropy is greater than the sum of the individual entropies. Okay, and this is a signature, okay, a super extensivity. Okay? However, when Q is greater than 1, which is the case of interest in seismology, okay, then, okay, the combined entropy, okay, becomes less than the sum of the individual entropies, and this would be a signature of subextensivity. Okay, then, therefore, okay, we are interested, okay, in subextensivity when talking about seismology. Okay, then what I want to make here a brief comment. Okay, I have when I started reading about Zali's entropy and his role in seismology. Okay, I was my attention. Okay, well, what caught my attention, okay, the most, okay, was the way in which, okay, the non-cumulative, okay, distribution function, okay, for the number of earthquakes, okay, with magnitude or energy greater than a threshold value, was fitting, okay, the observational data, so the catalog data, and this is very beautiful work, okay. Obviously, I'm not a truly expert in the field, but I want to express, okay, some ideas here, okay, which has been collected from other authors, okay, and I hope, okay, this, so my devotion to this field, okay, will continue in the future, okay. Then I want to express now, okay, that the point here is that, okay, we're interested, okay, in a generalization, okay, of the previous relation, okay, for the case, okay, of a continuous real function, real variable z, okay? Then, okay, here, okay, this P, okay, is the probability distribution of z, okay? And then the point here is how to determine, okay, this probability. Okay, the usual way is to throw maximization of the entropy functional, okay, subject to these constraints, okay, the normalization condition for the probability distribution, okay, and the generalized, okay, Q expectation value for z, okay? And then, okay, by making this procedure, okay, it is possible to, okay, to arrive to an optimized expression, okay, for the probability function, okay. We know that this is basically the Boltzmann distribution function for Q equal 1, okay. And then, and this YQ, okay, is the Q partition function, and beta Q, okay, is defined according to this expression, okay. Obviously, well, I wrote here Valianatos et al. 2018 in reference, okay, to an overview of this author, okay, where details, okay, of the derivation, okay, of these expressions are given in that paper, no? Okay, next, okay, I want to tell, okay, that Salis, okay, in 2009, okay, wrote a book, okay, where, okay, there are other forms, okay, alternative forms that could be used, okay, to fit the observational data. In particular, okay, I want to talk about this form, okay, which is one derived by Piccoli in 2009, okay, and used by Michas in 2015, okay. Obviously, most of the contributions, okay, in this field, okay, has been made by the Greek group, okay. We have a lot of papers and investigations, okay, of seismicity, not only in Greece, but in other regions, okay, worldwide, okay. And then also Zalis, okay, is a Brazilian guy, but I think it's of Greek origin, okay. And then he made a very important work, okay, in this field because, okay, in practice, okay, we know that earthquakes, okay, the mechanism of earthquake generation, okay, is a far from equilibrium process, okay, that cannot be described by the usual properties, okay, of the classical entropy, of the classical BG entropy. Okay, and then this guy, okay, is allowing us, okay, to understand more about the physics of earthquakes, okay, which is a primary line of research in seismology, okay, and also is of high priority in many seismic countries, okay. Then, continuing, okay, here, okay, this is a very famous picture, okay. I want to say the following, okay. It was possible, okay, to combine, okay, Zali's theory, okay, with seismology, okay, in principle, because Sotolongo, Costa, and Posadas in 2004 developed, okay, a model, okay, to explain how, okay, an earthquake, okay, can be produced. Okay, in part, okay, this picture, okay, which appears in many overview papers, okay, on non-extensive statistical mechanic approach, okay, to seismology, okay, is a schematic drawing, okay, showing, okay, two fault blocks, okay, one sleeping, okay, or one moving relative to the other. Okay, we see that the borders, okay, or the surface, okay, of both blocks are extremely rough, okay, in the sense, okay, that when these blocks move, okay, one relative to the other, then there is a stress, okay, accumulation, okay, either, okay, on the asperities, okay, of the surface, and on the fragments, okay, which hinder the movement, the motion of these asperities, okay. Here, for instance, B and A, okay, mark 2 points, okay, on the asperities, okay, of these block surfaces. And we see that these asperities can be hindered, okay, by the fragmentary material inside, okay, or, okay, it could contribute, okay, to the displacement, okay, of these fragments, okay. And this has been interpreted as the mechanism, okay, leading, okay, to earthquake generation, okay. And obviously the movement, displacement of the fragments, okay, or the fracture, okay, or one of the the asperities, okay, will release energy, okay, have the resulting consequence, okay, of an energy release, okay. Here, okay, these black arrows, okay, signifies, okay, motion of the fragments, okay, and R prime and R and R prime, okay, means a linear dimension of the fragments, okay. Okay, these fragments have a multifractal structure in the sense that they have a wide variety of sizes, okay? And then what Sotolongo, Costa, and Posada did was to relate, okay, the probability of finding, okay, a fragment, okay, of relative surface sigma, for instance, okay, using, okay, a non-extensive statistical approach based on Sally's theory, okay, with the distribution of energy, okay, with the energy distribution of the earthquakes, okay. Then in doing that, okay, and following the same steps for the optimization, okay, relating, okay, the probability density function, okay, with the SQ entropy, okay, they obtain, okay, this expression, okay, okay, for the probability, for, well, the fragment size distribution function, okay, this one here, okay, and then, okay, they also introduce, okay, these scalings, okay, where sigma, okay, means the relative surface, okay, of the fragment, okay, which scales R to the square, where R is a linear, okay, size, okay, of the fragments, of the fragmentary material inside the blocks, okay, and they introduce, okay, this other linear scaling between the release energy and the linear size of the fragments, okay, and obtain, okay, this expression, okay, which when plugged out in this equation here produces, okay, the energy distribution function given by this expression, where C1 and C2 are functions of the entropic index, okay. Now, defining, okay, the probability, okay, in terms of the energy release, okay, of the number of earthquakes, okay, with energy epsilon over, okay, the total number of earthquakes, okay, and integrating over, okay, this expression, okay, they define the cumulative number, okay, of earthquakes, okay, which is the cumulative density distribution, okay. This gives the number of earthquakes with energy greater than epsilon, okay, in this case, okay. And then, okay, okay, now relating the magnitude, okay, with the logarithm, or the natural logarithm of the release energy, okay, they ended up with this expression here for the cumulative distribution, okay, of the number of earthquakes with magnitude greater than lowercase m, okay. This expression was tested by themselves, okay, and it was found, okay, to fit very well, okay, data from some seismic regions, okay, pertaining to the Iberian Peninsula, the Andalusian region, and the Californian earthquakes, okay, for E greater than 3, okay. Then, obviously, there are many other expressions, okay. For instance, here, the Sotolongo coastal model was improved later on by Silva et al. In 2006, okay, by simply claiming, okay, this scaling, okay, where the energy, or release energy, okay, was proportional to r to the cube, where r to the cube, okay, has to deal with the volumetric size of a fragment, okay? And they obtain this relation where A, capital A here, is the proportional factor between epsilon and r to the cube, okay? And they obtain, okay, this expression, okay, which was a little, which has a little different, okay, from that obtained by originally by Sotomayor, Costa, and Posadas. And then, okay, by integration open, okay, the probability density distribution, okay, they obtain, okay, finally this expression, which is a very famous one, okay. Then next, Telesca, okay, in 2011 proposed, okay, this expression, okay, in terms of the magnitude, okay, which is the number of earthquakes, the normalized number of earthquakes, okay, with magnitude greater than a threshold value, okay, by simply relating the magnitude, okay, to the release energy by means of this scaling, okay? And then they obtain, okay, another expression which he thought, okay, that this would be more consistent, okay, with observation than this one, okay? And then there is another aspect very interesting, okay, by Daruni and Mary in 2010, okay, where, okay, inspired probably, okay, by the fractal nature, okay, of the fragmentary material between the sliding plates, okay, they propose, okay, the scaling, okay, and obtain, okay, this cumulative distribution function, okay, and then, okay, and then, okay, what is important here, okay, is if we look at these plots, okay, okay, and suppose that we pick up, okay, the BG entropy, okay, and perform the same optimization steps, okay, that we did for the Zaris entropy, we end up with this expression for the cumulative distribution function, okay? Then what is interesting for this plot, okay, that this expression, okay, fits very well, okay, the observed data or the catalog data, okay, only for very small magnitudes, okay, as shown here, okay? While the classical Gutenberg-Richter law, okay, which is an empirical law, okay, will fit, okay, the observed data only linearly, okay, for intermediate magnitudes, okay? While the any of these expressions, for instance, okay, the previous expression, any of these expressions, okay, for instance, any of these formula, okay, will produce, okay, a best fitting, okay, for all magnitudes, okay, as shown here, okay, schematically. Okay, then this is a very interesting point because I was highly attracted, okay, by the way, okay, this cumulative density distribution were fitting, okay, the observational data, okay, for real seismicity in many regions, okay, worldwide. Okay, and then, okay, I want to show some results, okay, well, what I consider to be some important results, okay, okay, obtained by previous authors. In particular, okay, here is Papadakis et al., okay, in 2015, okay, investigated, okay, the seismicity, okay, in Japan, okay, spanning from the period from 1990, okay, to 1998, okay. The interest was, okay, to see what happened, okay, with the Q entropic index, okay, in the proximity, okay, of the Kobe earthquake, okay, in 1995, okay. Then, okay, this plot shows, okay, the time evolution of Q, okay, of the entropic index, okay, and this, also the black, the thick black lines, okay, is the evolution of the time evolution of the Q index, okay, entropic index, while this, okay, represent, okay, the standard deviations, okay. Then we may see that from the period, okay, of April, okay, 1994, okay, to January, okay, 1995, okay, as marked by these vertical lines, okay, okay, the Q entropic index was rising, okay, progressively up to 1.5, and getting a peak value of 1.5. Okay, at this time, okay, the main shock occurred, okay, the earthquake, okay, took place, okay, and then what is interesting on this is that, okay, this can be interpreted as a preparatory phase, okay, for the earthquake, okay, and then this is a very important result because it's obviously that an increase of the Q entropic index, okay, is related okay, to the preparatory phase, okay, for an earthquake, okay. And then after the earthquake, okay, the Q value diminish, okay, until reaching a value of 146, okay, by 1997, okay. Then this is quite interesting, and this is obviously an important point, okay, in understanding, okay, the physics, okay, of earthquakes in part, okay, because earthquakes has been interpreted, okay, as a critical phenomena, okay, or near critical phenomena, because they exhibit power law scalings, okay, and very strong correlations, okay, and then the point is, okay, that this here, okay, when the Q reaches the maximum peak, okay, then we expect, okay, a strong, okay, seismic event, okay. Then next, okay, this is a beautiful plot, okay, where okay, this plot was reported by Daruni and Mary in 2010, okay, and the blue squares, okay, here, okay, is our data from the Iranian, okay, seismicity, okay, between 1996, okay, and 2005, okay, while the other curve, okay, correspond to the Californian, okay, seismicity, okay, between, okay, broad period, okay, between 1932 to 2008, okay, and then we can see how nice, okay, the okay, the cumulative, okay, distribution, okay, is nicely fitting, okay, the observed data, okay, and this, okay, this expression here was corresponded, okay, to this formula, okay, to this one, okay, they claim, okay, that this was much more accurate than the previous one. However, okay, I think, okay, I have only read one paper by Daruni and Mary, okay, and I haven't, and probably the most widely used expression is this one, okay, and also this sometimes, okay. Then, okay, returning to the applications, okay, this is another beautiful plot, okay, which obtained by Mijas et al. 2013, okay, when studying, okay, seismicity, okay, in the West Corinth Rift in Greece, okay. And then we can see that the dashed line, okay, is the GR law, okay, the Gutenberg-Richter law, okay, and the blue line, okay, is the fit, okay, to the observed data, okay, given by the symbols cycle, the empty cycles, okay, using this expression here, okay, they use this one, okay, this expression here, okay, and then it's interesting to see how, okay, this cumulative distribution, okay, fits the observational data very well. Okay, not only for Iran or California, but also in the Greek region, okay, in the Greek region. Okay? Then, okay, this is another nice plot, okay, obtained by Lucky et al. In 2018, okay, where they investigated, okay, the seismicity, okay, in the volcanic field, okay, of the Yellowstone National Park, okay, between 1996 and 2006, okay? And then we can see, okay, that also, okay, there is the fit is perfect, okay? So there is a perfect fit between, okay, the cumulative distribution, okay, obtained according to this expression again, okay? Sorry, okay? So to this expression, okay? And the catalog data, okay? For instance, okay, next, okay, since we are in Mexico, okay, well, I want to present some results, okay, reported by Valverde and Esparza in 2012, okay, where they studied the seismicity, okay, of 4 subduction regions, okay, in along the west coastline or Pacific coastline of Mexico, okay. This work, okay, they took account, okay, of Jalisco, okay, Michoacan, okay, Guerrero, and Oaxaca region, okay, and they presented, okay, this beautiful map, okay, about the temporal seismicity, okay, and then we can see that, okay, Jalisco and Michoacan regions, which are in the north part, okay, are much less active, okay, than the Oaxaca and Guerrero regions were. Okay, these dots represents, okay, main shock epicenters, the earthquakes epicenters, okay? And then we can see that most of the earthquakes, okay, happen to be about m=4, so magnitude = 4. Okay, and this is a very fortunate situation because otherwise it would be impossible to live. Okay, while strong seismic movements, okay, are much more rare, okay, than the ones, okay, with small magnitude. Okay, and then okay, Jalisco and Michoacan, okay, are less active regions compared to the Guerrero and Chiapas. Okay, pardon, Oaxaca. Okay, then okay, they obtain okay this okay, they obtain okay these plots here. Okay, okay, these are using okay this time okay this expression for the cumulative distribution function. Okay, it's this one. Okay, using this expression here. Okay, and then okay, they obtain okay values okay of Q for the seismicity okay in these regions between 1.70 to 1.63. Okay, then okay, what is important here is that we have submitted okay recently a paper okay to fractal and fractional okay where we have revisited okay this work okay, but now using the corrected Mexican seismic catalog okay, provided by the National Seismic Service, okay, and spanning okay the period between 2000 and 2023, okay, and we have used two different methods, okay, for the optimization for the fitting, okay, and obtain values slightly lower than those reported by Valverde and Esparza in 2012, okay, and probably the reason, okay, for this discrepancy, okay, in the values of Q, okay, may be due to the better instrumentation that has been used, okay, during the last 2 decades, okay, or at least in the last decade, okay. Such instrumentation, okay, could be more sensitive, okay, to the detection, okay, of low magnitude earthquakes, and that's why, okay, this lower the value of Q sometimes, okay. The value we obtained, okay, was between 1.6 and 1.5, okay, for the seismicity along, okay, the whole west coast line, okay, of Mexico. Okay, this including Baja California, okay, these 4 regions, okay, and Chiapas region, okay, in the south part, okay. Then, okay, I want to conclude, okay, my talk, okay. I hope, okay, this talk, okay, you are not get too bored about this kind of, okay, this list of relations and equations and expressions, but I want to conclude by saying the following, okay. Obviously, okay, for me, okay, this is a new line of research, okay. I hope, okay, to go deeper, okay, in this field, okay. It's a very beautiful field, and when I discovered, okay, Zali's entropy, okay, and in particular, okay, the Posada, okay, the Sotolongo Costa and Posada model, okay, and when I was reading, okay, many Greek authors, okay, which have contributed most, okay, to this field, okay, well, I became, okay, quite interested, okay, in this field, but I must say that this, why I have chosen this application, okay, because I think that this is the most visible result. Okay, obviously there are other applications, okay, which would be difficult to describe them in 40, 45 minutes, okay. However, okay, as I told you at the beginning of my talk, okay, I thank, okay, Dr. Alejandro Ramirez for having introduced me in this field, okay, and then I hope, okay, to continue okay, in these investigations. Okay, then I want to conclude with some brief remarks. Okay, first of all, okay, in the last 20 or more years, okay, there has been okay a large number, okay, obviously of applications, okay, highlighting okay the role of Zali's theory, okay, on the correct statistical framework for the description of seismic events. Okay, particular. Okay, as I told you, there are a big amount of papers. Okay, devoted. Okay, to non-extensive statistical mechanics analysis of seismicity in many regions worldwide. Okay, well, many seismic regions worldwide. Okay, including California, Greece, Italy, Turkey, Japan, etc. Okay, the fragment asperity model, okay, in my opinion, was a crucial model, okay, which links, okay, the non-extensive statistical mechanics formulation, okay, to the analysis of real seismicity, okay. And then, okay, I want to conclude here that Zali's entropy has many other applications, okay, to seismicity, okay, including, for instance, okay, the space-time description, okay, of seismicity, for instance, okay, plate tectonics, okay, okay, as a sub-extensive system, okay, combination of non-extensivity with natural time, okay, which seems to be providing, okay, an improved methodology, okay, for the observation, okay, of seismic data, fluctuations, and the non-extensivity in precursory, okay, electromagnetic anomalies, okay, in particular, okay, okay, here I know that there is Professor Sarlis from Greece, okay, which is an expert, okay, has introduced, okay, natural time, okay, and I hope, okay, that I couldn't come yesterday to his talk because I was busy, okay, with another commitment in the university. However, okay, I thank you, okay, for listening to me, and I hope, okay, that this has been, okay, fruitful for you, okay. Thank you. Okay.
So thank you very much for your very nice talk. I wanted to ask you the things which you described rely on the kind of power law decrease of the probability distribution, right?
Yes.
So the question to me is, the Thales entropy or the Thales distribution has that feature, but of course there are other distributions also possible which show the power law tail, which is what one lives from, right? Or is that a wrong impression?
Yes, well, I think it's only Zali's distribution, okay, showing this feature here, okay, because this cannot be described by other cumulative distribution functions, as I know, okay. Then it's basically, okay, due to the non-extensive mechanical statistical approach, okay, using in the framework, okay, of the Zali theory, okay, this is true. And what they did there, okay, was to follow, okay, the Q evolution. Well, what means is, okay, they take a cumulative distribution function, okay, okay, this cumulative distribution function is fitted, okay, to the observed data, okay, and then, okay, they have several time windows, okay, okay, along a period time, okay, and then they recover, okay, these plots, okay, and then they can study what happened, okay, before the main shock. Okay, in this case, before the earthquake, okay, and what happens later on, okay. This is the point.
Yeah,
Well, this is what I have understood at least.
Yeah, that is beyond what I had in mind. It was just
Yes.
about the power law tail of the
Yes.
distribution.
Yes.
Okay,
Yes.
thank you very
Okay,
much.
thanks. Well, okay.
Well, thank you very much.
Okay, questo no, piano piano. No, sorry. Okay, passo.
Okay. The next talk will be given by Luis Olivares Quiroz. Luis is, after earning his bachelor degree, he was in the Astrophysical Institute at Tenerife, España, collaborating with Pierre-Louis Palais in heliosismology. After that, he obtained his PhD in the Metropolitan Autonomous University, Campus Iztapalapa, and after a postdoc in the Institute of Physics at the National University of Mexico. His field of interest running from ultra low cold system, ultra cold gases. Okay, but also he was spending some time in several institutions like in Arizona University, en La Sapienza in Roma, in San Carlos in Brazil, Montreal University, and Warsaw University also. He has many papers in his topics of interest, particularly published in Biophysical Chemistry, European Journal of Physics, Journal of Low Temperature Physics, and Journal of Physics B. And for the current time, he is working at the Universidad Autónoma de la Ciudad de México, and also is the chairman of the Statistical Physics and Thermodynamic Division of the Mexican Physical Society. Okay, welcome, Luis, to Azcapotzalco campus, the Metropolitan University. It's our pleasure to is able to participate in this celebration. Thank you.
Thank you very much.
Thank you.
Can I use this one? Thank you. Okay, well, I'm going to switch between this micro and my natural voice. So you tell me if you can hear me. Well, I don't know, but you tell me. So thank you very much. Thank you very much for the invitation. I need a microphone. Okay, well, I'm going to try to do my best with both hands and trying to manipulate the micro and the pointer as well. Well, thank you very much for the invitation, Ruben, a very dear friend of mine from some time ago. And well, the first thing that I want to say in just a couple of minutes is that I'm very thrilled to be here at UAM Azcapotzalco because, Jose Inés, hello, how are you doing? Because UAM is my alma mater. I graduated in the physics department at UAM Iztapalapa. For those who don't know, the UAM University has several campi. So this is one of them. Iztapalapa is another one. So this is in the north part of the city, and Iztapalapa is in the southeast, southeast, I guess. So I was graduated in physics in the physics department at UAM Iztapalapa. So I'm very fond of this university. I really love this university. And now that I was walking on the alleys, I was remembering some of my time here as a, well, not here, but at UAM, but graduate student. So thank you very much. And well, thank you even more, Ruben, for that kind of presentation, which is very on the survey. Well, I'm just, I've been in somewhere around, but the more important things is that I'm now at the Universidad Autónoma de la Ciudad de México, which for those who don't know is one of the newest public universities in Mexico, if not the newest one. So it has already 20 years, it's a very young university, but we are there and we have a complex system department there and a physics department, so I'm there. And well, I also happen to be the chairman of the Statistical and Thermodynamics Division of the Mexican Physical Society. So I'm very thrilled to be here today, and here is my email if you want to contact me. Well, thank you very much. I put my clock here, so I will try to run on time because it's almost time to lunch. So I'm not trying to bore you too much with calculations. I want to give you a very general picture of a very couple of things. But I'm going to talk today about something that really thrills me, and it's something very new. Well, I consider it's very new. Here in Mexico, worldwide, it has around 20 years, maybe a decade, well, maybe a decade more, 30, 40 years. And it's the interface and the mixture of math, physics, and molecular biology. It's what is called in many places biological physics. Some other people say biophysics, physical biology. It depends on who you talk to. But it's something that I'm very, very excited because it's something that when I was a graduate student, I was trying to move there, but no, it's here. So exactly, when I was a graduate student, I started to study this kind of thing. So I was a physics student doing physics in a physics department, but I was very interested with my now deceased ex-former supervisor, which is very well physicist, is Leopoldo Garcia Colin, was Leopoldo Garcia Colin, which is very famous here in Mexico. But we start to move to this field. And what is this? It's essentially trying to apply physics methods, particularly those of statistical physics and thermodynamics, to try to understand these entities. What are these entities? These entities is what we call enzymes or proteins. In molecular biology courses, they know them very well. It's just from the physical point of view, they are just macromolecules, are huge molecules. And here I put some images to try to understand the scale of this. This is a water molecule, and this is represented here as a very small red dot. So this in green is the enzyme, the biological macromolecule, the protein, and the dots in red are the water molecules. So these molecules are inside fluid, water normally, and then we have these enzymes that have very interesting properties from the biological, but also from the physical point of view. For instance, 90% of the enzymes have catalytic activity. That means that they participate, mediate, or inhibit many chemical reactions. Most of the chemical reactions that you already know that happen inside the body are mediated by these kind of molecules. So that's very important. So that's the reason why we should, in every field of science, put more attention to them, particularly in physics. So let me tell you what I'm not going to talk today, but it's important to tell you about this. It's something that I started 10 years ago, more or less, and was to trying to understand something that is called protein folding and unfolding in enzymes. It's a very tough problem, actually, in molecular biology and in physics. And the idea is simple, but not simple, is that usually there is this biochemical pathway in which a protein is synthesized inside the cell, and then it forms a native structure called a three-dimensional structure called native structure, in which the enzymes is capable to produce or to inhibit or to participate in any given chemical reaction. But if for any reason this biochemical pathway is not achieved, then the enzyme falls into a different state. That different state is called misfolded state. And the reason of that, the importance for that, is that these misfolded proteins have been recognized to participate in many, many neurodegenerative diseases. One of these is the so famous Alzheimer's disease. We now know that Alzheimer's disease is usually based on a molecular level in the misfolded pathway of these proteins, particularly the tau protein in this case. So that's why it's very important to understand that this is a artistic representation. And well, this is actually how in an experimental and X-ray diffraction experiment looks on how these proteins aggregate to form filaments, and these filaments block the synaptic connections in neurons, for instance, in this case. So that's very important. So, but that's not what I'm going to tell you. It's just a brief introduction to that. What I'm going to talk to you now is how relevant is to try to identify what is so-called the active sites in enzymes or active sites in biological macromolecules. What is that? Well, actually, Here is a very famous picture. You have seen this many, many times, very surely in the past 5 years. This is a SARS-CoV particle, viral particle. Here we have the famous spike S protein here in red. And well, this is an influenza virus particle, which is a related virus. But the idea here is that, I don't know if you have this known previously, but the name H, X, and Y in influences means two proteins, actually. Means the name of the H is for the hemagglutinin protein, and the N is for the neuraminidase protein. So this combination means that there are 15 variants in H and 9 variants in N. So we have all these variants in viruses in the case of influenzas. But why I'm telling you now this, because these are two examples of proteins, just proteins that participate in binding the viral particle to the cellular receptor on the surface of the cells. That's exactly what, well, not exactly, but very similar to what protein spike S does. So that's what we try to understand. We try to understand which sites of these proteins, in this case spike S, or in this case hemagglutinin and neuraminidase, are in binding to the cellular cell, to the cellular wall. So now I'm going to go a little bit into math and a little bit into physics as well. So from the physical point of view, what is happening here is that we can see these images here is actually very descriptive. We have the enzyme here. These are these holes. Actually, the name is pockets, but yeah, you have these pockets, these holes that represent the active sites. We have here this substrate that is going to be binding here. So the enzyme, after this binds, changes slightly in form, and then a chemical reaction occurs here, and then the products of this reaction releases. So this is the role of the active site of the enzymes. Is where another substrate binds to the molecules. Biochemical catalytic reaction occurs, and then some products are released. But the actual, from the physical point of view, is in this process is actually what changes is the activation energy barrier of this process. It's the same energy barrier, but I mean, it's the same difference here, only that this energy barrier is the difference in this process. This is what the biological enzymes actually do. So they are very important even from the physical point of view. So now, some math. How are we going to try this? So this is the biochemical and, well, biomedical relevance of this. So we're trying to tackle this with this mathematical approach. What is this? This is a graph, mathematical structure. I always have this joke with my students because in Spanish, graph and plot could be the same thing, but it's not an XY plot. It's a graph. So a graph is a mathematical structure, which is essentially a set of n nodes, which is depicted here in blue, and a set of edges which connect them. Why is this a structure important? It's a mathematical object in itself. So there's a lot of work of mathematics, of mathematicians around this structure. There are a lot of theorems, books, et cetera, around this topic. And why is this important? Because this is a mathematical tool that enables us to try to quantitatively analyze the units are the interactions between them. So it's another way, very different from physics. There is no Hamiltonians here, no other physical equations. It's just a mathematical structure. So someone would say, well, is there any relation of graphs and molecular biology? Actually, it is. There is a lot of literature, but this one is very nice, actually. So it's a review. So graphs in molecular biology is already a very, very interesting topic. So, let me show you this graph, which is very interesting for me. There was a time where there was no one interested in graph theory, or well, at least very few people. Actually, this goes very far from the work of Leonhard Euler. The problem of Leonhard Euler of the 7 bridges in the Königsberg is actually a graph problem in mathematics and in applied mathematics. So it comes very far in time. But well, in more recent times, actually there was no many people interested in that, except at this point in the 1940s, 1950s actually. Well, this is a zoom of this graph, and then the interest started to increase with the advent of computers, essentially, because many of these mathematical models can be implemented now in computers, and we can do a lot of work here. So graph theory and network theory are both synonyms in this case. So this is the central slide of today. What I'm going to show you is how we are going to start from the three-dimensional crystallographic structure of an enzyme. This is known experimentally by many different experimental means, for instance, X-ray diffraction, but there are another ones. So we have this information about the enzymes. We are going to map this into a three-dimensional network. This is very important. This is not a two-dimensional usual network. This is a network which preserves the physical distances between atoms and the physical locations, as you can see here. So this is a three-dimensional network in which each node represents one of the C-alpha carbons of the primary structure. This is a quartz grain representation. Actually, we can go further into this, and we can try to put all atoms in there. We can do that as well. But in the first approximation, we can do a quartz grain representation, and then we only took the central C-alpha carbons of the backbone of the enzymes. And then we are going to do two things. We are going to do an static analysis of the connectivity of the network, and on the other hand, we are going to put a set of random walkers moving around and jumping around the different nodes, and we're trying to count the number of nodes that is more visited in a given period of time, or in the long time limit. I mean, it's as an stochastic process, actually. The stochastic process in the sense, not of a stochastic differential equations, in the sense of Brownian particles jumping between the nodes that are connected with a given probability, given by the inverse of the number of links any node has. So this is, well, what I just told you is this, essentially. We have to come up with a probability transition matrix, which means what is the probability that a particle jumps from a given node to another one, and this is related to the inverse of the number of connections, so they have equal probability. Of course, this is a first approximation. We can do much more complicated than that, because we can consider Levy jumps, which are jumps that can move very far into the network, but that's another story that I'm going to tell you, hopefully some other invitation, but not now. So, well, we are coming up with this, with this probability transition matrix, which satisfies this equation, because once a particle is in one node, it has to go at some place mandatory. So the sum of the rows have to be unity, as this one. For instance, the particle, if he's here, has to be here, or has to be here, or has to be here. So there's 1/3, 1/3, 1/3, and that's for every row in the matrix. So this is actually, maybe you can recognize this. This is a Markov chain, actually. This is the definition of a mathematical Markov chains embedded into the network. So what we're doing here is to set up a Markov chain, to embed a Markov chain structure into the network. No? So this is essentially what we're going to do, and then a little bit of more mathematics in the model. We're going to calculate the mean first passage time matrix, which enables us to count the number of steps to reach node J if we start from node I. So this is going to be called emission, and this is going to be receptor, and we're going to count the number of steps to links that the particle needs to arrive to that place. And this is not a symmetric matrix, because it's not the same number of rows. So H is not a symmetric matrix. So now applications. We started with some enzymes, and here's, for example, one example that was presented to you in the first slides. The first slide is 1YAS, which is an oxidoreductase, which is a cryptic name. Maybe we are not biologists like me, but well, we can talk a little bit more what this protein does. But the idea is that we can calculate this process for this network, and we can identify that there are some nodes that has the least number of steps to arrive them. So if we start in any node inside, arbitrarily any node inside the network, there are certain nodes that are the most quickly arriving nodes I mean, the most quickly nodes to arrive there. So that's very interesting because when we start to look for experimental information about which the active sites of these enzymes was, we have these plots. In blue, we have the experimental results of this database, of which are the active sites for these enzymes marked here, and here in red are the results of our calculations. So when we, well, this one is very nice actually. When we make a comparison between the experimental results shown here in blue, our theoretical results shown in red, we have these results shown in black, which is almost an 80% plus of match between these experimental results and our predictions. So we repeated this for many enzymes. This was at the very early stages of this. We said, well, maybe that's some good coincidence here. So let's do that. And with some of my students, I started to look in the protein data banks for many proteins and try to repeat this procedure. And we say that this percentage was even low because in many cases, the percentage of match was around 90%. So that was very interesting for us. And this is a more detailed representation of how the network looks like, actually. You can see the nodes, but the most interesting things here is that there is no just a single link that connects this, but there are different, and this means the different degree of interactions that any nodes can have with the other ones. So, well, this is a PDF, it cannot work because this is a simulation that a student from UNAM that was working with me did. This is a parallel line of research, but in this simulation, the red particle starts to jump around all the network inside the whole network. So if you can check out for more details, you can see a paper in the Physical Biology Journal, which is a very nice journal in this team, and we are very happy with this paper. So now, in the last part, I'm going to talk to you about some recent applications that we have been doing with SARS-CoV-2 Mpro enzyme, which is a very interesting enzyme related to the SARS-CoV virus. Why? Because this enzyme is the main protease of this virus, which means that is the enzyme that cuts the polypeptide chain, and that enables that each segment of the polypeptide chain can do what it has to do whenever the virus gets inserted into the cells. So it's very important. And I don't know, particularly the students, there are students interested here, don't know how or what allosteric sites means in this case in biological context, but it's very important, and I'm going to tell you a little bit of that. So this is the three-dimensional structure of the SARS-CoV main protease Mpro. This is here, you have the letters of each of the residues, and this is a representation showing in colors the polar and hydrophobic characteristics of each. So, well, this is more a little biology, but the stuff is that here we're going to make from this three-dimensional structure, we're going to construct this three-dimensional network, and this is the superposition of how it looks in this case. So this plot is just very informative because it's a graph of distances inside the network. So you can see that there are some nodes that are more close to others. You can see the scale. The diameter of this network is around 13 steps, which is this 12.5 means, which means that the two farthest nodes in this network is around 30 steps to arrive. And you can be, of course, 1, 0, etc., etc. So this metric is symmetric. This is not the H metric. This is symmetric. This is the Cartesian distance matrix. So there are a couple of things that comes interesting here. We calculated two things. The H by row. So we are going to measure the number of steps needed to arrive to a given node from any other node in the network. This is what H means. And in blue, you have the 10 minimum values. And in red, you have the catalytic nodes of these enzymes. It's experimentally known that these enzymes has two catalytic residues, which are located at positions 41 and 145. So this is this is these two in red, here also in red. And in this case, is a quantity that is known how many times a node is visited in a long time simulation. I mean, if we put a set of particles there and we count the number of times a given node is visited, then this is quantity. So we again have this active site here, very near the top. You can see that this is very frustrated profile. I mean, there is a lot of maximum and minimums very near. So it's very difficult to start to establish a unique maximum because, well, for instance, these two ones are very close and these ones here are two actually superimposed, etc. But what is the most interesting result here is this slide. And the slide is the following. So our analysis showed that there are, well, we have the catalytic site. I mean, the site where any other compound may block this enzyme by attaching to that place. So this is the H41 and cis-145. So they are represented here. But as a result of this analysis, it shows that there are two additional residues that are not reported in the literature yet, and they have special particularly properties here. For instance, we can measure the closeness centrality measure, which means how close is a given node. And we see that, well, the catalytic residue has these values compared to the maximum. The maximum is actually the 128, but it's very interesting because very near the catalytic site, 145, there is the 146 and 147, which is just one residue away. So this has very high values. This form a pocket because this has 0.903, 0.963 of the maximum value. This means this marks that this is a region, actually. It's not just one single, but there is a region in which there is happening this phenomena. On the other side, we have that here, for instance, in the number of, I mean, the H row result shows that we have this value for this other catalytic residue. So there are two additional residues that stand as the maximum values for these quantities, not exactly the active size, but this one. So the question is, what is happening biologically at these residues? Is happening anything interesting or they just, I don't know. So what is going to happen? And it turns out when we talk, I've been talking with some guys and people and friends in the Faculty of Medicine at UNAM and the Bioscience Department, that actually I didn't know that because, well, I'm a physicist, so I can know everything. But actually, this one is actually one of the candidates for allosteric site in this enzyme. Our colleagues in the biomedical science know that very well, but I didn't know until I talked to them very recently. So just for summarizing and trying to do some perspective on this, well, the idea that I want to let you here today is that the identification of active sites in biological enzymes is a very important thing, actually, because if you can block selectively these active sites, you can block the enzyme and all the catalytic reactions that may come after that. So here we have two levels of description. We have an static analysis in which we only calculate the static properties of connectivity and topology of the enzyme, of the network. But on the other hand, we have a dynamical process running on the network. We have a set of random walkers, and we calculate stochastic properties of these random walkers. It's the equivalent of what is usually done very much in crystals and some lattices. You have a regular lattice, so you can put particles moving, but in a specific regular spots. So here we don't have that symmetry because this is a physical amorphous three-dimensional network, but the idea is very similar. So the results is that we can, in the specific case of the SARS-CoV and protein, we can identify residues that stand up as very interesting places in the number of visited places, but maybe we can establish a connection between them. And two interesting things is that we are working now with some students in trying to expand this, not only to consider normal random walkers that diffuse immediately to the neighbor, but can jump in a long range, which is called Levy process. So there are, as we always know in physics, there is only a second part of the story. We have always first order, second order, third order things. So there are second and third order kind of centrality measures we can apply. I'm not going to talk to you about this now because it's another long story, but we can work with the adjacency matrix of this graph, and we can derive centrality measures of second and third order. And just to finish, I'm going to show you some current work with my students, taking advantage that there are some students here that maybe could be interested in this kind of things. It's a very nice thing. It's math, it's physics, and it's biology. So, and it has many applications. So this is a poster of one of my students. We are doing not blocking. We are now in the process of blocking certain residues and see how the effect propagates. And what we have found here is that the propagation is long range. We can block one thing here and the effect goes very far inside the network. So that's very, very interesting because the effect is non-linear, it's expansive. So we can say, well, I'm going to block here so the effect remains here very locally, where that is not the case. The effect can propagate in a very long range. So, well, this is part of my students in my group. These are some of the posters that we have been putting in some events. These are some events that I am part of the organizing committee that has to do with biophysics in Mexico. We started these kind of things in 2015, 2017, 2019, 22. Actually, it was 21, but we had the COVID, so there was no event until 22. And well, here my contact for particularly students, if you want to touch me for talk and maybe consider some opportunities. Very recently, one of my students had this award from, she presented her thesis results. So she got an award of mención honorífica in the Mixbal Award for best thesis on these kind of things. And well, this is a picture of the events that we have been doing. Particularly, we did the 2002 event at UAM, at Casa del Tiempo UAM. It's a very nice place. So very surely you know that place. And for students, again, this is a book that I have written about this kind of things. It's no equations, just physics, just math, very elementary level, very interesting stories. You will learn and enjoy, I think, a little bit about things. And just an epilogue, very thing. What are we doing now? We are now moving to a set of viral proteases, which are very important from the medical point of view. Maybe the slide is not very good, but here I marked down some viral proteases, very similar to the SARS-CoV, which are of biomedical interest, related to HIV, to hepatitis A, B, and C, to obviously SARS, MERS, to herpes simplex virus and all kind of viruses that have this kind of viral enzymes. So, well, I think I'm gonna finish here. Thank you very much.
Okay. So, questions? Okay.
Thank you. Two questions. The first is, hence you don't consider that the distances between the carbons change, because obviously when there are some actions in the pockets, something changes inside the enzyme.
Yes, I know. It will depend. Actually, there are enzymes. Well, in biology, happens a very interesting things. It's not like physics. In physics, we have very strict rules about how things happen. But in biology, I have learned that when you find one thing that does one thing, you can always find another thing that does a different kind of thing. So what is the stuff here? These are the three-dimensional structures that are a result of our energetic minimization process. I mean, so we run first an energy minimization process and make sure that more or less they are energetically stable. So at that kind of level, things doesn't move anymore. But you're right in the sense that you can find some previous structures in which they are still stabilizing previously. So we have not reached that stationary state yet in those enzymes. But in these ones, yes, we have.
Thank you for the very nice talk. I would like to ask you, how can you achieve blockade when you have levy flights?
Well, that's a good point. We haven't considered that two combinations, that combination yet. I mean, we haven't been blockade when the particle just moves to the immediate neighbor. In that case, we have done yet. But the other one we haven't. Maybe I'm open to ideas, but I need to think about it because it's a little bit more difficult. Yeah, no, thanks to you.
Any other question, comments? Another.
Yes, I say that too. Do you find some active places inside the enzyme, or all are in the surface?
Yeah, thank you very much. There are two types of active sites. Binding sites, which are usually on the surface because they have to bind with an external molecules. And you have another ones that are called catalytic sites. And these are usually inside pockets more buried inside the core of the enzymes. Because what they do is not bind, but produce a catalytic reaction moving hydrogen bonds inside the molecule, moving the structure. So there are ones that are on the surface and ones that are inside the core, more near the core of the enzyme. Yeah.
Actually gonna, I think, ask two questions. You ignored one earlier. The bond lengths are different, but you still go according to, is it bonded or isn't it? Your random walks. Do you ever try to consider bond length?
Yes, well, I didn't mention because there was not too much time, but the way in which we put the links between nodes is defined in this way. We put a sphere of a given radius in each of the atoms and count how many atoms are inside this sphere. This sphere has a very particular value, which is around 8 angstroms, which is twice the covalent bond between two C alpha carbons. So there is a criteria to define how the connections are embedded in this structure. I mean, so distances are considered because you have to put a sphere in every atom in moving and count how many of these atoms are inside that sphere, and that's how you define the adjacency matrix of the network.
Until that answer, my initial belief was just, is there a bond or isn't there? But that was not the way you make your networks.
It's actually, you map the multi-dimensional structure and start moving on some cages inside one of the atoms and see how many of the atoms are inside that cages. So in that sense, you see how they interact with the others, because it's not just the immediate connection that we are looking, analyzing. We try to do how the other, maybe if I show you a picture. It's not just the carbon connections. I mean, for instance, I guess this one works. There might be some atoms, let's put this, that is not covalently bonded with this one. Could be, because they're not in the sequence. But in this scheme, this atom may be inside the sphere of interaction of this one. So it's counted as having an interaction of some physical sense in that case. It's not just covalent bond interactions in this case. It's more than that. Exactly. Exactly. That's it. Yeah, it's based on physical distance, but it can include amino acids that was not originally physical. I mean, how to say this? Let me see if I can find a figure at the very beginning. Maybe this one works. Yeah, maybe this one. I mean, there is the backbone of the enzyme, which is all the atoms that are covalently connected between them. So consecutive 1, 2, 3, 4, 5, I mean. So if we unfold that, we arrive with a one-dimensional spaghetti, I mean. So that is just the immediate with the previous and so on. But this kind of things counts how many of these atoms, not only in the previous and in the forward, but in the physical three-dimensional vicinity of there are. So they are counting some kind of interactions that were not coded in the original primary structure of the enzyme. Hope this helps a little bit. But we can talk a little bit more if you like.
Okay. And one more question here, Juan Carlos.
Thank you very much for your talk. Here I am. It's just a comment. I was wondering that you are considering when you have a node in your Markov chain and you want to jump to another node. If you have, for example, 3 possibilities, you have the same probability to jump for each one. But why? Do you have a biological inside that have the same probability to jump? Is it just an assumption? Thank you.
Otherwise, the problem should be just a jump from high complexity in the first place. So we want to stay in the first approximation for now. But in the future work, we are going to consider level flies or some other different kind of movements. Well, actually, no, because from the biological point of view, there's no particles inside the enzyme jumping. It's just a mathematical model to try to. Actually, this is also very useful to try to measure information propagation in a network, in a general network. I mean, this is the idea behind. So if you see this, just forget about biology. Just see this as a network of individuals propagating a disease or a social communication, social information. This is how information can jump also in the very first nodes. Maybe, yeah, maybe that could be.
There is more questions. Well, nice.
So I'd like you to go back to one of your figures, because my understanding is that you do the random walk. Oh, yeah, an extra microphone's great. Thank you. You do your random walk, and then you take the positions where I would call it the stationary distribution, but your long time walk spends a lot of time.
Exactly, that's what it
That
means.
was that was your red color, I think.
Yeah,
And then you had another color.
yeah.
Can you remind me how that?
Yeah, there was actually just 2 colors, red and blue. The
Yeah.
blue were the absolute maximums for that plot, which are not necessarily the biological ones. The red ones are the biological active
And
sites.
how do you get the biological?
There is experimental information about that.
Oh,
people have-
you need to take a biologist.
Yeah.
Okay.
Yeah, well, it's not a bad thing, actually.
I get the impression that you consider the structure of your conglomerate up there as fixed. It does not change along the way. But in many cases, during the catalytic reaction, the surroundings will open up, close. Some of your pictures showed some of that, but that's not the impression I got from your explanations. So how much does actual morphing of your enzyme play? And also what by doing some morphing, you are prepared to send that processed molecule onto some other side, so that you're that things have to come in sequence because the enzyme molecule has changed. Have you considered any behavior of that nature?
Yeah, of course. And that is the allosteric thing, actually. Well, here we're considering what is called in biology the apo structures, which means there is nothing attached to it. It's just like the raw structure. It's just the three-dimensional structures with no other thing attached, compounds, inhibitors, promoters, etc. It doesn't change generally. So when you attach something to it, it can happen two things. It can change structurally or it cannot. Actually, there are a lot of papers that said that many enzymes doesn't change structurally. But let's assume that there is some structural change. So we are analyzing now a set of compounds attached to this molecule, and we observe that there is a change, and we're trying to consider that into our calculations. But yes, we are consider that kind of things when it happens, and in this case, actually, this is happening in the MPRO enzyme. So we are analyzing the compounds attached to this structure, but here I just presented the raw structure, I mean, with no other compound attached.
And I think that there is a last, no, Juan Carlos? Okay, but
So
well,
one tequila for each question, right?
yeah. No,
No, it's okay.
no, I
Just
have
kidding.
I have a question.
But you're going to buy us some tequilas, right?
Ah, okay, and okay, let me for Juan Carlos.
No, it's okay.
No, well, no, we will talk later because I am interested in the computation of hidden times and the invariant distribution for this network. Hidden times and resident times are closely related to recurrence times, and you can build the invariant distribution of recurrence times, no? Or the recurrence plot, for example, similar to the plot that you given for the distance, for Euclidean distance. And this recurrence plot allows to compute a lot of statistical properties of the network. No? And there is a software already implemented for these computations. But okay.
Yeah, just a brief, thank you, Ruben. Just a brief commentary on that. Yes, you're right. This is a discrete mathematics approach, just random walkers moving on the red, but we can implement differential equations here, also moving into and it's like a amorphous lattice. I mean, in that sense, we can implement a set of differential equations on that node. And then the adjacency matrix says to which nodes we're connected, and it's going to move the information or whatever we can think about. Thank you very much. I'm very thrilled of the interest that has come here. Thank you very much. Gracias a todos.